polygons. That's what you say when your parrot flies out of its cage, right? Anywho, alright, we're going to be looking at polygons, what they are, and all kinds of classifications of different polygons. Looking at figures and some word problems, all kinds of stuff with polygons. What is a polygon? A polygon is a closed planar figure made by 3 or more line segments joined together. So in other words, the figure you can draw on a flat surface. It's closed in, so all the edges are connected. And you have to have at least 3 line segments to make it, but you can have more line segments than that to make one. Each of the line segments is called a side, and the points where those segments meet are called vertices. Each one's called a vertex. If you take the sides and the inside, like if you were to color it in the interior region, the sides and the interior region together are called a polygonal region, whereas the polygon is the figure itself made up of line segments. And then, specifically, a regular polygon is a polygon where all the sides are the same length and all the interior angles are the same measure. Here's some different polygons. Remember, you have to have at least 3 sides, 3 line segments. If you have at least 3, you have a triangle. If you have 4 connected, you have a quadrilateral. Some famous ones you're probably familiar with are square, rectangle. You've also got rhombus, trapezoid. 4 line segments joined together make some type of quadrilateral. 5 make a pentagon. You've probably heard of the Pentagon building in Washington, D.C. 6 make a hexagon. It's that little shape that ends up in a beehive's honeycomb. 7's a heptagon. 8's an octagon, like a stop sign. 9's a nonagon. 10's a decagon. 12's a dodecagon. And you can have all kinds of numbers of sides. 20 has a specific name of icosagon. So there's some of the different names. The lower number of sides are the more frequently encountered ones. You've probably, on this day, up until now, you've probably never heard of a dodecagon or a icosagon. Or who knows, maybe you have, but most people haven't. Alright, now when we're looking at these polygons, there's all kinds of problems that come up that need us to not just deal with the sides and how many there are, or necessarily the lengths, but also the angles on the inside of the polygon, and what's going on with those. And there's all kinds of patterns related to this. Let's start with a triangle, and let's see if we can try to just look at some patterns together. I know that most of you are familiar with what a triangle looks like, 3 sides. See how they're connected. The points where the line segments come together are your vertices. Stop. Oh my god, I don't know how to make that stop doing that. Previous semesters I never had that problem. Also don't want that. Alright, so you got 3-sided figure, that's a triangle. The interior angles here, the measures of the angles add up to 180 degrees. And if you have some kind of quadrilateral, let's say a rectangle or a square or any kind of quadrilateral, the interior angles add up to 360. But what happens when you have something like a pentagon? What do the inside angles add up to then? In a quadrilateral, you can use a square and see that, oh, you got 90, 90, 90, 90, that's 360. Rectangle, you've got 4 90-degree angles, that's 360. But even if the angles aren't right angles, in a quadrilateral, the inside ones are going to add up to 360. It's just the way it works. In a pentagon, in fact, I already know what they add up to. They add up to 540 degrees. In a hexagon, I know they add up to 720 degrees. All 6 of those angles. In a heptagon, I know they add up to 900 degrees. Normally I ignore these random lines it puts in, but for geometry I can't because then it changes what the figure looks like. Oh, my word! And so forth. So anyways, so taking a look at these, I was wondering if you spotted a pattern. Do you see any sort of pattern as far as the number of sides in the polygon versus what the inside angles add up to? You know, we have 3 sides here, 3 angles. We have 4 sides, 4 angles here. 5 sides, 5 angles here. 6 sides, 6 angles here. 7 sides, 7 angles here. Tell you what, octagon, let's go ahead and draw that in. Maybe a stop sign. That's going to add up to 1080 degrees. You know, 8 sides, 8 angles here. Do you see any kind of relationship between the number of angles and how much they add up to as far as their measures? You know, like the 7 angles here adding up to 900 degrees, the 8 angles here adding up to 1080. If you want to take a minute to try to figure out the relationship on your own, feel free to pause the video and think about it before moving on. Because in the next slide, or in the next few minutes, I'm going to reveal what's going on here. Alright, well if you decided to pause it, now we're back. If you didn't decide to pause it, now we're moving forward. And we're going to look at why is it that the sums of the angles are what I just listed here. And one thing that might help you is the fact that a triangle has 3 angles that add up to 180 degrees. That fact is the basis for why all these other angle measures come out to what they do. And I'm wondering, well, how? How does a triangle have anything to do with those other ones? Well, sometimes when a figure is too complicated to work with as is, it helps to divide it up. And maybe work with the shapes that you get after you divide it up. In the case of a quadrilateral, you can always divide it up into 2 triangles whose angles add up to 180 degrees. This, 1, 2, 3, those 3 angles add up to 180. 1, 2, 3, those 3 angles add up to 180. And yet, the 3 angles from this triangle and the 3 angles from that triangle are the 4 interior angles of this quadrilateral. These add them up, 180, 180, you get 360. Okay, drawing from the same vertex on the pentagon, you can do that and make 3 triangles. From the hexagon, start from the same vertex and start drawing triangles by doing segments out to every other vertices that are out there. And you can make 1, 2, 3, 4 triangles. 7, you can make 1, 2, 3, 4, 5 triangles. With 8, you can make 1, 2, 3, 4, 5, 6 triangles. So, you know, starting with 1 triangle, you have 1 times 180 degrees. But with the quadrilateral, you have 2 triangles. That's 2 times 180 degrees. Pentagon, 3 triangles. That's 3 times 180 degrees. Hexagon, 4 triangles, 4 times 180 degrees. Heptagon, 5 triangles times 180 degrees. Octagon, 6 triangles, times 180 degrees. So that's how you can see how much the interior angles add up to. Do you see a pattern too with the number of triangles versus the number of sides or interior angles in the figure? We've got 3 sides, 3 angles, 1 triangle, 4 angles, 2 triangles, 5 angles, 3 triangles, 6 angles, 4 triangles, 7 angles, 5 triangles, 8 angles, 6 triangles. You see a pattern here? If you saw that the number of triangles is always 2 less than the number of sides or angles, you are correct. That is true. And knowing that, we can then figure out the sums of the interior angles for any size polygon. What if we have a polygon where there's 100 sides? Well, you don't have to sit there and draw out the polygon with 100 sides. It would take too long. No need to. You don't even have to draw the triangles or anything like that, because you're going to be able to make 98 triangles. It's always the number of sides with the number of angles minus 2. And each of those triangles has angles that add up to 180 degrees. So you can take that, think 98 triangles times 180 degrees, and you find out that a 100-sided figure has angles that add up to 17,640 degrees. Isn't that crazy? So here's the formula. The sum of the measures of the interior angles of an insided polygon is n minus 2 times 180. However many sides there are, minus 2 times 180 degrees. And that'll tell you how much it adds up to. Now another interesting thing is if you have regular polygons, remember, regular polygons, all the angles are the same. All the sides are the same length, all the angles are the same measure. For a triangle, each angle you have 180 degrees total, divided by 3 angles, you're going to get 60 degrees for each angle. For a quadrilateral, square, you got 360 divided by 4. Each angle is 90 degrees. For a regular pentagon, you had the 540 degrees divided by 5 angles. Each angle is 108 degrees. Now you might be looking at this and going, wow, each angle is getting bigger and bigger, which makes sense because the more sides you have, the more you're spreading out. You have to spread it out in order to connect the sides together. Let's see, we had hexagon. That was 720 divided by 6. Gives you 120 degrees for each angle. But you know, there is a limit. It's the measure of the angle can never go past a certain, never reach or go past a certain number. I'm wondering if you might know what that is. Let's go back to our 100-sided figure. 100-sided figure had 17,640 degrees total, right? 17,640 degrees. Divide that by 100 angles, and you get 176.4 degrees for each angle. So all that is definitely a bigger angle than the one for the hexagon. You can keep going, increasing your number of sides over and over again, and you will never get to or go past 180 degrees. Anybody guess that? Anybody guess 180? I wish I could hear your responses, but I can't. Because if you think about it, 180 degrees would mean that the sides would have to make straight angles. And you start trying to connect sides with straight angles, and you're never going to make a polygon. You're never going to be able to close it in. It's just going to make, if you keep going, it's just going to make a line segment, or eventually infinity, it'll make a line. So that's not going to work. So your angle measure has to stay under 180. It can be 179.9, and that'll work. It'll make it kind of very gradual connection and going around. It'll look more circular. The more sides you add, the closer and closer to a circle you get. But you can never actually, as a polygon, get to 180 because then you'll have a straight. It'll be straight and it won't ever connect to make a closed figure. Alright, moving on. Let's look at some specific polygons and some of the different classifications they have. Starting with triangles. Triangle is the polygon with 3 sides. There's different kinds of triangles classified based on the angles and classified based on the sides. Classifying a triangle based on angles, in an acute triangle, all angles are acute angles. So every angle in that triangle falls somewhere between 0 and 90. So they're smaller angles. In an obtuse triangle, you're going to have one obtuse angle in there. The others will be acute. The others have to be acute. And again, we're talking about planar geometry. The rules change if you start studying spherical geometry or elliptical or hyperbolic, other kinds of geometries. The rules change. We're just talking about planes, flat surfaces. Okay, so here's an example of an obtuse triangle. Has an obtuse angle in there, an angle that's more than 90 but less than 180. Then the other 2 angles have to be acute, so that all 3 will add up to 180. Right triangle, again in planar geometry, has 1 right angle. The other 2 are going to be acute. And again, like on a sphere, rules change. You can have more than 1 right angle. You will have more than 1 right angle. And on a pseudosphere, you'll have no right angles. One other little thing just wanted to point out. When you're looking at triangles, your largest angle, opposite of it, will be the largest side. Like the angles and their opposite sides are kind of proportional, for lack of a better word. So I got a right angle, the right triangle, the right angle is the largest angle. So the side opposite of it, the hypotenuse, is the longest side. If your smallest acute angle will be opposite your smallest side. Like if you have small, medium, and large, small angle across from small side, medium angle across from medium side, large angle across from large side. It'll always work that way with these triangles. And if all 3 angles are the same, then all 3 sides will be the same too. Let's talk about that a little bit more here. Alright, you can also classify triangles by sides. Isosceles have two equal sides. But if you're dealing with an isosceles with 2 equal sides, based on what I was just telling you about angles and sides being related, angles opposite are also going to be congruent. Equilateral has 3 equal sides. And what happens there is with all 3 sides the same, all 3 angles are also the same. And then scalene has no equal sides. So the three sides are different. Largest angle is across from largest side. Smallest angle is across from smallest side. Medium angle is across from medium side. Alright, so that's triangles for you. And then another one's quadrilaterals. I want to point out what some of the quadrilaterals are. Trapezoid you'll often see drawn kind of like this. On a trapezoid, two sides are parallel. Parallelogram you'll often see drawn like this. Not the only way to draw it, but you'll often see it drawn this way. Opposite sides parallel. So both pairs of opposite sides are parallel. Also, opposite sides are equal in length. A rhombus you'll often see drawn like this. Looks a lot like a parallelogram, but in a rhombus, not only are opposite sides parallel, like in a parallelogram, but all four sides are equal in length. A rectangle you often see drawn like this. It does have four right angles. Opposite sides parallel. Opposite sides equal in length. Also, all the angles are right angles. And then finally you got your square. Not only has four right angles, but also all four sides are the same length. So opposite sides are parallel. All four sides equal. And angles, all angles are right angles. Separate these so that when you read this later you can see what goes with what. Now there's some relationships between the quadrilaterals. You might have noticed as I was writing down these features of each quadrilateral, some of this stuff kept repeating itself. You had your parallelogram. That was one where opposite sides are parallel, opposite sides are equal in length. So that's a general name for a quadrilateral where you have opposite sides parallel, opposite sides equal in length. Now you have other quadrilaterals that could be also classified or looked at the same way. Looked at as with different names. Rhombus. Both pairs of opposite sides are parallel. Also, both pairs of opposite sides are equal in length. So a rhombus is also a parallelogram when you look at the definition. By definition of a parallelogram is a quadrilateral where opposite sides are parallel. Rhombus definition includes that. Parallelogram, opposite sides are equal in length. The rhombus definition includes that. So a rhombus is a type of parallelogram. So a rhombus is a type of parallelogram. Alright? So you had your rectangle. A rectangle is also a type of parallelogram because the definition of a rectangle includes everything from the definition of parallelogram. Opposite sides are parallel, opposite sides are equal in length. A square. A square is also a type of parallelogram. Opposite sides are parallel, all sides are equal in length. A square is also a type of rhombus. Because in a rhombus, opposite sides are parallel, four sides are equal in length. That is true for a square. Opposite sides are parallel, all four sides are equal in length. If an entire definition fits a figure, then that figure can also be classified that way. This square can also be classified as a rectangle. Because according to rectangle's definition, opposite sides are parallel. That's part of the square's definition. Opposite sides are equal in length. That's part of a square. If all four sides are equal, then opposite sides are equal. All angles are right angles. That's part of a square too. Now, you can't always say that a rectangle is a square because rectangles can have sides that they don't have to have all four sides equal, whereas a square does. But a square is a type of rectangle. Type of parallelogram, a type of rhombus. Trapezoid. It's kind of its own thing. It's a quadrilateral. According to some books' definition, only two sides have to be parallel. Other book definitions, at least two sides are parallel. And if you use that definition, then all of these others can fit with trapezoid too, but we're just going to go with the traditional thought that just two sides are parallel. All depends on how somebody defines it. I'm trying to look through this and think, is there anything else that fits some of these? Yeah, square is a type of rhombus, but a rhombus doesn't have to be a square. A square is a type of rectangle, but a rectangle doesn't have to be a square. Rectangle doesn't have to be... Let's see here. Yeah, rectangle and square require that the angles are right angles. So although they're the type of parallelogram, not all parallelograms are rectangles or squares. I think that about does it for those relationships there. Okay, moving on. Now we're going to get into some more more application type problems. Now that you've seen the different classifications, some of the different polygons, etc., if you are working on a problem where you're dealing, it can be polygon or not, but if you're dealing with two polygons, similar polygons are polygons that are the same shape, but may or may not be different sizes. The angles are the same, which gives them the same shape, but the sides are proportional, which means they could be equal or they may not, as long as you can set up a proportion with them, with all the sides. Similar figures come up when, and for example, with maps. A map is drawn to scale. So when you look at a map, the shape of the land or the ocean or whatever is the same as it is in real life, like in reality, but it's drawn smaller. So all the angles are the same, but lengths are different. Lengths are shorter on the paper. And they do it in a proportional way to retain that shape. Let's look at an example with similar figures. And let's see what is meant by the whole, what to do with this proportional sides business. Alright, let's say you have one quadrilateral. Looks like this. And it's quadrilateral ABCD. This quadrilateral, you have side AB is 9 units, side BC is 6 units, and side CD is X units. And then you have a bigger version of the same shape, and you're told that these two are similar. Similar, it's like this little squiggly symbol. So you have A complement, B complement, C complement, D complement. Alright, A complement, B complement is 15 units, C complement, D complement is 10, B complement, C complement is Y. And you want to find the missing links. Figure out how long side CD is and side B complement, C complement. Well, you can set up proportions to figure this out. You know side AB and you know side A complement, B complement. So you can set up a ratio of 9 to 15 for those. And then using the figure on the left first again and the figure on the right second again, you could do BC over B complement C complement. And you can solve that proportion by cross multiplying. You get that Y is 10. You can also use your 9 over 15 to solve for X. In this case, CD is X, C complement, D complement is 10. Cross multiply. X equals 6 when you solve. So as long as you know that they are similar, you know that corresponding angles are the same. So angle A and angle A complement are the same measure, B and B complement are the same measure, C and C complement are the same measure, and then D and D complement are the same measure. You know that. And since they're similar, you know the sides are proportional, so you can always set up a proportion. But just make sure when you set up your proportion that you're consistent with how you do it. Like if you do smaller figure over larger figure here, you gotta do smaller figure over larger figure there. And there's some variations in how those proportions can be set up, but be consistent with how you set up your fractions. Alright, let's look at maybe one more example with that. Say, okay, Steve is buying a farm, needs to determine the height of a silo on the farm. Steve, who is 6 feet tall, notices that when his shadow is 9 feet long, the shadow of the silo is 105 feet long. How tall is the silo? And my diagram will not be drawn to scale. Here's the sun. Talked about sun's rays earlier. Well, we got the rays of the sun coming down like this. And that ray will keep going in that direction until something stops it. Something that stops it could be the Earth. Now, if we happen to have a silo standing right here, stopping the sun's rays from coming down and hitting the Earth, you're going to hit the silo. What's going to happen? There's a little door to the silo. What's going to happen is that you're going to cast a shadow. And they said this particular silo, we don't know how tall it is, but we know that it casts a shadow of 105 feet. Okay, at the same time, Mr. Steve's out here. And let's say he's standing somewhere where the sun's ray is coming down at the same angle. He's 6 feet tall. We know that. We can measure him. And we find out that his shadow that's cast by blocking the sun's ray is 9 feet long. So the silo has the 105-foot long shadow. Steve has the 9-foot shadow. Steve is 6 feet tall. We want to figure out about the silo. Well, what's happening here is we have similar triangles. We're going to assume the silo is standing straight up and down. Silo is X feet tall, cast a shadow of 105 feet. Steve, we're going to assume is standing straight up and down and not leaning. He's 9 feet shadow, 6 feet tall. How do we know these are similar figures? Well, the sun's ray is coming down and hitting at the same angle, whether we're talking about the top of the silo or the top of Steve's head. So this angle here is congruent. And the way this is drawn, if the sun were to keep going and hit the earth, in both cases, it would hit the earth at that same angle here and here. And then the silo and Steve are standing straight up and down, so we know we have right angles here. So corresponding angles are the same measure of the same type of polygon, so we know then that these are similar. So what we can do is just set up proportions, set up a proportion, and solve it. Like in this one, what I'm doing is I'm doing height of silo over shadow of silo equals height of Steve over shadow of Steve. So I did height over shadow, silo is one ratio, Steve's the other. Cross multiply. And you get the x equals 70. So apparently this silo is 70 feet tall. And that's how you do it. Now congruent figures are a category of similar figures. And congruent figures, not only are the angles the same, the corresponding sides are the same too. And you could still technically say that the corresponding sides are proportional. It's just the proportions are going to come out to ones. But still, you can say that because the sides are the same length, and you can set up ratios and they're going to equal each other. If you have a scenario with congruent figures, it's actually pretty easy to finish filling in whatever's missing. Let's say you have figure, this quadrilateral here with quadrilateral ABCD. And then you have another quadrilateral. It's just rotated basically. A complement, B complement, C complement, D complement. Redraw that, because I can't have random segments going off, because then it just changes what shape it is. It doesn't make sense. Especially if somebody's reviewing the notes later and not watching the video. Alright, that'll have to do. Alright, we've already got some of it labeled. We've already got some of the side lengths, some of the angles labeled. So let's fill that information in. And we're told that these two are congruent. Erase that. That's a little symbol for congruency. These two are congruent, so corresponding angles are the same. If we know the angle D is 70 degrees, then D complement also has to be 70 degrees. If we know angle B is 130, B complement also has to be 130. If C complement is 50, C has to be 50. If we don't know A or A complement from the figure, but we do know it's a quadrilateral, So all of them 4 have to add up to 360. We've got 180, 250, so we need what? Another 110. And that'll give us the 360. And since they're congruent, corresponding sides are the same. AB is the same as A complement B complement. BC is the same as B complement C complement. AD is the same as A complement D complement. The only one left we don't know how to do is CD and C complement D complement. Not enough information given here, especially not at this level. Fun stuff, right? Congruent figures are more fun than similar. Alright, a couple more problems I wanted to do with you guys. Moving on from after similar and congruent. So you're going to see some problems like these, and I just want to make sure I do one of each. You're going to have some figures where they draw some lines and fill in some of the information, and it's up to you to find like the missing angle based on what they've given you. Just to warn you, this is not drawn to scale. You might start with something like this, where they tell you, okay, this angle is 57 degrees, this angle is 27 degrees, find this angle here. All right, let me pick a different color. That way later you'll be able to see different color in there. Start filling in what you know. You can't immediately go to X because you don't have enough information yet. But what you do know is, like for instance, right here you have vertical angles. This is 27. This one has to be 27 also because of vertical angles. Right here, these three lines mean that these angles that are side by side making up that line have to add up to 180. So next to the 57, the adjacent angle has to be 180 minus 57. So we have to have 123 right here. 57 plus 123 is 180, which would make this straight line here. And hey, we've got a triangle. We know that the triangle angles have to add up to 180. And we've already got a 123 and a 27, which is 150. So that remaining angle in the triangle has to be 30. And then finally, these two angles here make that straight line, 180. So subtract 180 and 30, and you get 150. So you're going to see problems like this. You're not going to be able to immediately jump and get the answer. You're going to have to start filling in stuff you know. It might take you off on a little journey for a bit, but eventually it'll bring you back around and get you to what you're trying to find. One more of those. Let me change my ink color back to black. This is a different shape, different figure, but it's the same kind of concept. Let's see, in this one you're going to have two parallel lines. You have line 1, line 2. You know that line 1 and line 2 are parallel to each other. And then they are intersected with two transversals. I'm having the darndest time drawing with this, but two transversals. In your book or in my math lab, basically drawn straight. And you're only given limited information. So like in this case, you're given this angle here is 59 degrees, this angle here is 70 degrees, and that's it. That's all you're given. So you got to fill in the rest. You got to find all the other angle measures. Let me change my ink color again. So start filling in what you know. Across from 59 here, this is a vertical angle, so this also has to be 59 degrees. Across from 70 here, this is a vertical angle, also has to be 70 degrees. You've got a triangle, has to add up to 180. So see what it takes after having 59 and 70 to make 180. You need 51 degrees right there. Let's see. Down here we know, okay, this has to be 51 because of vertical angles. This has to be 129 because of the straight line there. It has to be 180 with the two together. This has to be 129 because of vertical angles or because of the 180. This has to be 110 because these two have to add up to 180, or these two have to add up to 180. Same thing with this one, 110. Vertical angle is 110. So far so good. This transversal here, try to pretend you don't have the other one right now. For that transversal, what do we got here? Alternate exterior angles. You got a 70 there. This one's going to be 70. Alternate interior angles, 70 here, 70 there. Let's see, straight line. You got 70 and 59 already, which is 129. So this here has to be 51. And that's so same thing with this one. There you have it. There's all the angles. So I use things like alternate interior, alternate exterior, vertical. You might be able to use corresponding. All those different relationships. You're going to use those and help you to fill in the rest of them. Alright, well there you go. I will be continuing with this geometry stuff in the next lesson, but actually that'll start the next unit. Remember, first Unit C stops with 8.2. Unit D picks up and does 8.3 and 8.4. Alright, so I look forward to seeing you again. Thank you for joining me.